Hey Jude, welcome back.
Hey, yeah, thank you
Very
very
excited to
much.
hear about this next part, and yes, I'll get out of your way and please take us away.
All right, thank you very much. All right, well, let's get going with the C++ memory model. Now, before we get into these two sessions, I will say that these are probably the hardest technical sessions that we're probably going to cover. Yeah, don't panic. Please don't panic. But all right, so C++ memory model. Let's get into it. So first of all, what we're going to do is a quick refresher on the stack versus the heap, and sort of like what the memory model looks like in C#. Then we're going to look at how it differs in C++. Something that I hope to drill into everybody who's watching by the end of this talk is everything is a block of memory, and the sooner you the sooner you think of everything as a block of memory, the easier C++ is going to be. How memory gets allocated at the assembly level when the compiler actually compiles your machine code. What does it look like? How things get copied when they're passed into functions. And then we're going to talk about copy and move constructors and a few other bits and pieces that we need for how memory works. So a quick refresher on the stack versus the heap. So the stack, also known as the call stack, is where you have your memory for local variables, right? And so the stack size for a function is known at compile time. If I have a function with, a single integer on a 64-bit machine, that integer is going to be 8 bytes of memory. So when the compiler calls that function, it knows that it needs to move the stack up by 8 bytes to make room for that memory. And so in the memory of the computer, you will have the base of the stack. You'll have the stack pointer, which moves up and down as you're going through, as you're calling functions and as they're returning. The stack memory is allocated at the application startup, and it basically extends deeper the more calls you make. And this is why you get stack overflow if your call function gets too deep, because you run out of the pre-allocated stack memory that you had at the application startup, and it doesn't have any more space. So then you're just oh well, I'm out of stack memory. So that's the stack, that's the call stack. Then we have the heap, which is dynamically allocated at runtime. This is where if I want to, in C#, if I create a new class, the class ends up on the heap. You can dynamically allocate memory of any size as long as the operating system has enough memory available. Importantly enough, if you allocate memory here, you also need to release it because, well, at least in C++, there isn't something that's going to do that for you. So that's the stack versus the heap. If we look at the C# memory model, it's defined by the type of thing. So for classes, when you construct them, they are allocated to the heap. So they go onto dynamic memory. They're never on the stack, right? They're always nullable at runtime. Technically, newer versions of C# have what they call non-nullable reference types, but they're actually still nullable at runtime. It's just a compiler, a pure language feature that tries to prevent you from making them null, but it's actually totally allowed to still make them null at runtime. They're on the heap. They're always passed by reference to functions, and what I mean by this is if you create a new instance of a class in C#, and then you pass that through to a function, the function has the thing it has that class you initialize. It doesn't get a copy of it, right? If you modify that class inside that function, then you'll see those changes reflected outside the function where you passed it in. In contrast, in C#, structs and value types, they are allocated on the stack when they're local variables or parameters. They can be part of the heap if they're inside a class object that's allocated on the heap. They're never nullable. So if you have a struct, you can't set. If you have a field that is that has a type that is a type of struct, you can't set that field to null. And in C#, they're always passed by value, which means they're always copied. If you make a struct and you fill it out and you pass that struct as a parameter to a function, then C# will copy the entire contents of the struct when it passes in. And any changes you make to the struct will not be reflected in the caller because you're working on a copy. So in C#, the memory model of things is defined by the type of thing that you're using. In C++, the memory model is defined by the usage. So the only difference between classes and structs in C++ is that structs have public members by default, right? If you have a struct and you say like int a inside it, then if it's a struct, that a is going to be public member by default. You can access it anywhere. If you use class instead of struct, it's private. Otherwise, they're exactly the same. The usage, how you use the type, defines where the memory is allocated, whether things are copied or passed by reference, etc. If we look at, so the size of classes and the size of structs is basically just the size of all their members added up. So in this case, we're defining my class, and it's 32 bytes in memory. Again, everything is a block. Everything is just blocks of memory. So when we create my class, whether it's on the heap or the stack, it's going to take up 32 bytes of memory. And that's because the standard string or the string class from the C++ standard library is 32 bytes. Now we can use our my class in two different ways. We can put it on the stack with our stack allocated local variable, where we just got my class stack allocated. We could put it on the heap by having a pointer and saying new my class. So the new operator is what is basically like, reserve me enough heap memory for the size of this class. So it will go and say, hey, operating system, allocate me 32 bytes of memory. And then initialize my class in that location and then return me the memory address. And then on the stack, all we've got is the 8 bytes for the pointer, right? Because to store a memory address on a 64-bit machine, you just have it's just 8 bytes, right? Which is 64 bits. The important thing to note here is that we're using the same type, my class, in two different ways. We're using it on the stack and we're using it on the heap. And then we also, in C++, because there's no garbage collection in just straight C++, we have to call delete to say, delete this thing from the heap that we are no longer using. Otherwise, we get a memory leak. Something I just want to point out real quick is that this code here is also valid. So pointers don't have to just point to the heap. You can make a pointer that points to the stack. So in this case, we're taking a pointer and we're taking the address of something on the stack, and we're saying, okay, this is the pointer. Like the pointer is going to point to a memory address in the stack, because the stack is just memory, like the heap memory, stack memory, the memory locations of functions. It's all just blocks of memory, right? So we can point the pointer wherever we want. We can also make references to the stack as well. And in fact, we're going to use references to ensure we don't do unnecessary copies on function calls later on. Make sure I'm covering the notes. Oh yeah, something to point out here is if I take this pointer, the address of the stack allocated variable here, right, and I take this pointer and I store that pointer somewhere, and then main returns, it's important to note that that pointer is going to be pointing to a location on the stack, but it's not actually going to be that memory isn't being used for stack allocated. It could be being used for a completely different function. It could be pointing to memory in the middle of another class that happens to be a local variable in a different function, right? So just like taking the address of the pointer, taking the address of the stack allocated thing, you have to be sure that, like, if you're going to do that, that you're not going to be using that address longer than the actual stack allocated memory is going to be alive, which is just for that function, call. Otherwise, you're going to get like garbage nonsense. You probably won't get like a segmentation fault or a crash, because the stack is allocated up front, and the operating system doesn't care if you just access in the middle of your own memory and you access it in a way that's just nonsense. It doesn't care. The only time that you're actually going to see an application crash is if you access outside of memory that you actually own, right? If you try and access a memory address that you haven't allocated at all. But the stack, since the stack is allocated at startup, operating system will let you read as much garbage out of it as you want. And it's totally fine. I want to stress this point. Everything's just blocks of memory. The sooner that you think about things like this in C++, the easier things will be. Objects that you allocate on the heap, they are just blocks of memory. Local variables are just blocks of memory. You can, when you're first learning how to do C++, I think it's probably more helpful to think of things in terms of blocks of memory rather than thinking about like, oh, this object's going to call this function on this other object, and this object's going to reference this other object, and you think about that. I think it's probably helps you to get a grasp on the fundamentals sooner if you think about like, oh, this class has a pointer which is 8 bytes of memory, and since I'm allocating this an instance of the class on the heap, there's 8 bytes of memory on the heap that happens to point to it. Like, try to think about what it looks like in memory when you're allocating classes and that sort of thing. So then you have a much clearer idea of what's going on. And then as you get used to thinking in that sort of mode, then you can sort of shift to the higher level abstractions, because it's important in C++ to really have a good idea of the fundamentals of like what's going on underneath the hood, because C++ has no guardrails, right? Like, I mean, it has some guardrails, right? But it's not going to stop you from shooting yourself in the foot, right? It's like, oh, you want to read this random memory address that you happen to have allocated, but actually doesn't logically make any sense. Here, have some total garbage, and you're going to like run your program. You're like, why is this string like random characters? Because, you know, that's just what happens to be in memory at that location, and you can totally read it, but like it's just nonsense. So, you know, good luck. All right, now we're going to use Godbolt. So Godbolt is an excellent tool. It is a compiler explorer, and what it lets us do is look at what the machine code is the compiler is actually producing for our code. So first example, I'm going to grab this link. I'm just going to chuck it in the Discord for people to load up. Alrighty. I didn't want it to be in the StreamYard tab. Can you go to the right one? Thank you. Cool. And I need to get my notes on another screen for a second. Cool. So, yeah, nonsense. I love it. Okay, cool. So we've got a nice little test class here. We've put a standard library string into it, which is 32 bytes, and an int, which is 4 bytes. So because we're compiling for 64-bit, I think, but an int is going to be 4 bytes, so it's a 32-bit integer. A long is a 64-bit integer. So that's why it's 4 bytes, because if you take 32 bits and you divide by 8 bits per byte, you get 4 bytes. Which means the overall size of ftest class is 36 bytes. You need 36 bytes in memory to store an ftest class. So the first thing we're going to do is we are going to comment out this, like down here on this test class on stack function. Let me know if, actually, you know what? I'm going to make this a bit bigger so people can see stuff. Let me know if the text is unreadable, and I will try to make it bigger for people. So first thing we're going to do is we're going to uncomment this test class on the stack, which means that test class on stack is going to allocate memory for an ftest class. The first thing you might notice is that the constructors and destructors for ftest class are now present. And what was happening before is the linker was basically saying, you know, we got default constructors and default destructors for ftest class, but then the linker was being like, oh, you're not actually using any of these functions in the final executable, so I'm just going to remove it. You don't need it. You're not using it. It's fine. Don't worry about it. But now, because we're using the class and we need to actually construct it and destruct it as part of the test class on stack function call, it's like, cool, I need to create the constructor and the destructor. And if we look at what these constructors and destructors are basically doing, you will notice that the constructor for ftest class is calling the constructor for the string. And this is what makes the string value here be initialized to an empty string, right? C++ by default is adding a default constructor for us that will do the correct initialization for this string class. Later on, we're going to come down. We're going to look at what is happening here. So inside test class on stack, we are now basically saying, so the RSP value here, this is what we call, these are all registers, right? So your CPU, you have your main memory, and then the CPU has a bunch of registers, which is like what it actually works on. And you can load memory from the main memory into registers and vice versa, and you can send it back and stuff. So, but there's a register here, which is RSP, which is the stack pointer. And so what we're actually doing is we're subtracting, which is kind of moving up or down in memory. Yeah. It's basically moving the stack pointer by 48 bytes and saying, cool, I want to move the stack pointer by 48 bytes, so I have 48 bytes for this function to work with. And then we've got a little bit of maths here, which is basically just saying, okay, we've moved the stack pointer up by 48 bytes. And then at the start of that 48 byte segment, we are now going to call the ftest class constructor on this fresh memory that we've just allocated on the stack, right? And then because we don't do anything with this, because we don't do anything with ftest class, we basically go straight into the destructor, right? And because this is a stack allocated variable, the destructor is called for us, right? The function allocates the memory for the stack allocated variable, and it releases the memory for the stack allocated variable, right? It basically pushes the stack back down again when the function call returns. Yes, was there anything else? Oh yeah, so remember how we said ftest class was 36 bytes in size? And you might notice that we're allocating 48. This is going to be basically down to like debugging information, metadata that the compiler wants to reserve. Oh, actually, something I forgot to do for this talk is put the slides in the Discord. Liam, if you could grab the slides from Google Drive and put in the memory model PDF into the Discord, that would be great. Okay, cool. So let's look at step 3. So we've done stack allocation. We can see how the compiler or the machine at runtime is going to like move that stack pointer down, allocate the memory. We are going to comment out the heap allocation. So this is down in step 3. Again, you will notice that the constructors are now present. You'll notice the destructor isn't present, right? Because we're allocating this on the heap, right? But we're not actually calling the destructor anywhere. So the link is like, well, you're not calling destructor. I don't need it. Even though this is a memory leak because we aren't actually releasing the memory. Now, how does heap allocation work, right? So if we go down here, we're still moving this stack pointer, but we're moving it by less now. We're moving it by enough to store the pointer. The pointer being the 8 bytes here. We need enough stack memory to store the pointer on the stack. And then what we're doing after we've made room for the pointer, we are then going to call the new operator with the amount of bytes we want to reserve. So in this case, the compiler is saying, please reserve me 40 bytes for this ftest class, and call the new operator, and this is going to give us a memory, a dynamically allocated memory on the heap, 40 bytes. This bunch of stuff here, I think I will cover it in a moment, but it's basically just zeroing out the memory that we've just allocated in the heap, because the heap can be pointing, like the operating system is going to give you a chunk of memory from just the available memory, but it could just be random garbage in there, right? It's not well defined. The operating system is not going to zero stuff out for you. So we zero out stuff out here. We then call the constructor at the memory location that we've just allocated, right? And then we don't call it the delete. We haven't called delete. We're going to do that in step 5. We haven't called delete, so we just finish and just delete the memory. C++ is just like, sure, whatever. Okay, cool. All right, step 4 is non-default constructor. So we're going to leave this commented commented in, yeah. And we are going to override the default constructor. So at the moment, C++ is generating a default constructor for us. If we declare a parameterless constructor, this is going to replace the default constructor. And it does, because we haven't actually defined any code here, it's still going to do nothing. But what's really interesting here is that, notice it doesn't clear out the memory for us anymore, because the constructor is not the default constructor. It's expecting us to do the work required to set up the state of the class so it makes sense. Now, you will still get the string initialized properly, but this int, instead of being 0, this int can just be random garbage because we're not actually setting it to 0 anymore when the class is constructed. And this applies, this is the case on the heap, but it's also the case on the stack, right? Because you might have called functions deeply and then come back down. Like if you've returned to functions and you're calling again, And if you don't initialize your memory to like 0 or something sensible, then it could just be random garbage left over in the stack from previous function calls. It's fine. We don't zero out memory because why would we zero out memory if we're going to initialize it properly? Like, that's just more work we don't want to do. If you actually want the default constructor, you can do equals default. And then you'll notice we get our zeroing out back. All right. And finally, we're going to delete some memory from the heap. So we're going to actually free up this class that we're putting on here. You will notice that once we uncomment this and we now delete it, hey, guess what? Our destructor is back because now we're actually using the destructor. We come back down here and we look at what this does. It basically takes it basically resolves what's stored in the pointer, right? Because we've put the address of the memory that we've allocated in that new ftest class is going to be stored in the pointer. The pointer has the memory address, and so then we're basically getting the memory address from the pointer, and we're calling the destructor on that memory address, and that is what it's going to like tell all of our, nested fields to also do their destruction. And then we're saying, hey, hey computer, please delete the memory that we allocated at this address, and it's 40 bytes long. And now we've properly cleaned up our memory usage. All right, that is how are we doing for time? Oh boy, we're in trouble because I have more slides to go through. I'm gonna have to be really quick. Okay. Yes. All right. Another Godbolt example. Right. So, it is some pointer math. Let's find out the address of things. So in this case, I've got the program output on the right here. And we're basically allocated this ftest class. It's got 3 ints in it, right? We've initialized them to 4, 5, and 6. And we're just printing out the value of the first int, right? So we've got m, we're saying, give me the first int out of this pointer, or out of the ftest class that the pointer is pointing to. But where is m in memory, like the thing we've allocated? Where is that? We can actually find that out. So if we can actually find that out if we go and uncomment this line. This will tell us the memory address, and we can see that the class has been allocated at this particular memory address, right? And if we say, well, what's the address of the first int, the first field in the class, right? And it turns out that this is exactly the same because, again, everything is just blocks of memory. The class doesn't need anything at the start of it other than just the things that are in it, right? It's just 3 ints in memory. So it makes sense that the first int is the same address because it's just a block of memory that holds 3 ints in it. What's the address of the second int, right? Well, it is exactly 4 bytes after the first int, right? Because again, it's just this block of memory. You've got your first int, and then you've got the second int that comes immediately after it. Just making sure I'm all right. So we know the address of the first int, the second int. Can we use some pointer math, right? Because again, the pointer is a memory address, and a memory address is just really just an int. Can we just modify what the pointer points to and read the second int without actually knowing where second int is, without actually referencing the second int field? We can. So if we get into this code here, all right. So we're getting the address of the first int, right? So this is just a memory address. It's a pointer to, it's just a pointer to an int, right? And then we're adding 1 to the pointer. Now this is not adding 1 to the integer, right? This is adding 1 to the pointer. And you might be thinking, but hang on, if it's a pointer and we want to get the next int after it, shouldn't we be adding 4 bytes? When you add a numeric value to a pointer, it's basically incrementing by the size of the thing that the pointer is pointing to. So because it's pointing to an int, this is actually going to increment the memory address by 4 bytes. And then we dereference the pointer, which is actually saying, give us the thing the pointer is pointing to. And now we get 5, which is the value in second int. We didn't refer to it at all, and it's totally fine because everything's just a block of memory. It's all totally good. Pro tip, if you want to do horrible things in Unreal Engine and you want to get at private fields that you shouldn't be able to access, guess what? Everything's a block of memory, and you can use pointer math to get at the engine internals that you're not supposed to have access to, because if you know the offset, you can just be like, cool, well, I know this private field in the class, in like the Unreal Engine header class, is 48 bytes after this public field. So I'll just get the address of this public field, add 48 bytes, and there we go. We can access it like it's public. Don't do this unless you really want things to be very brittle, because obviously if the layout of the class changes at all, your code's going to break and you won't get any like compiler checks, but you can do it. You can do it. Oh boy, we are halfway through and I am running out of time. Okay. Okay, yes. That's our whole presentation. Go away. Oh god, presentations. Okay, so if our usage defines whether something is on the stack or the heap, and by value by reference, does that, I'm just going with that weird, yeah. Does that mean that we can copy anything by default? Yes, we can copy anything. And this means that every single class and every single struct by default has a default copy constructor. And we're going to look at this example. I am very glad that people in the Discord are realizing the implications of everything's a block of memory, and you can just access whatever you want if you know where the location of it is. That makes me very happy. Okay, cool. So, yeah, okay, cool. So we've got this ftest class, we've got a string inside it, we've got an int inside it. We are going to put an instance of this on the stack. We're going to say hello, set the int to 5. And then what we're going to do is we're going to do a copy. We're making a second stack allocated variable. This is not a reference. This is another ftest class on the stack. And we are saying it is equal to A. Now, if you think about what this means, right, everything is a block of memory. So we can't make B just a pointer to A because we haven't declared a pointer, right? We actually have a second ftest class on the stack. So what we need to do is we need to actually copy the contents of A. And C++ will generate a copy constructor by default for you, right? So in this case, we have, again, now it's here because the linker says now we're using it, right? So we have this copy constructor. It takes in a reference to an existing ftest class, and then it is basically going to do all this stuff here is basically work to copy the state of one ftest class into another. Something that's noticeable is that here for this string, guess what? We are calling the copy constructor for the string, because you'll notice that this is a const reference, right? Parameter now. Instead of the parameter string we had the string constructor before, it's now the copy constructor for the string. So we're also copying the string as well. So we're copying the string, we're copying the value of the int, and that means we then get a full, complete copy of ftest class. I think that's good. Okay. Back here. Okay. Every asterisk class and struct gets a copy constructor. So, okay, so not every class and struct. Some types are classified as a trivial type. And these are types where the compiler knows that you can just copy the entire... They're types where the compiler knows that to make a copy of it, all you have to do is copy the literal bytes that are in memory, right? None of the types within the class or the struct are non-trivial themselves, i.e., none of them require calling a copy constructor to get the correct semantics. Copying the memory block is much faster than calling copy constructors all the way down through all the fields. So the compiler will choose to just do this straight memory copy if the type is a trivial type. That means you won't see a copy constructor called in the assembly for trivial types. And trivial types are, let me see if I'm gonna. Trivial types are basically so all of like the really basic types. So ints, longs, pointers, because their memory address, they're basically just an integer. They're all trivial types. You can copy an int by just copying the memory, right? It's the same thing. If you look at the string class, though, the standard string class, it's non-trivial, right? It has a non-default copy constructor, which makes string non-trivial, which then makes the class that uses it non-trivial, right? So this triviality trait basically propagates all the way up. Something to keep in mind when you're using because obviously the C++ compiler will generate these default copy constructors for you, is that they are often incorrect. The default copy constructor is not aware of, it doesn't understand roll pointers, right? It will just copy the pointer, but that's probably not what you want, right? Because if in your class you've allocated memory on the heap with new and you've got a pointer to it, and then the thing that has that pointer gets copied all over the place, it's really hard to know when to call delete, right? When do you know when the last usage of it is? More examples. All right. Okay. Let me. Yeah, cool. So this code's a little bit more complicated, but basically we've got a test class. It holds a pointer to a string. Now, because the only field in this class is a pointer to a string, it is by default trivially copyable, right? Because we can make a copy of our test class by just copying the memory. However, this has problems. So if we uncomment this down here, right, we are going to get a crash. And the reason is if we actually look at what this code is doing, right, I'm going to try and get through. Yep, cool. So we've basically set up our class. We've initialized it to the null. We've got a set string class. This is allocating a string on the heap because now we're doing new standard string and the value. Here we're setting it to hello. So our A has a pointer to a string on the heap. That string happens to contain the value hello. Now, when we go down to our copying, which is all the way down, I think it's, no, it's here. You'll notice this copy is literally just like these two assembly instructions, right? Because the only thing it's got to copy here is actually a pointer. It's not copying anything other than just the string pointer, because the class itself doesn't have any memory other than what's inside it. So it's just copying this pointer. And now we have both A and both B have the same pointer inside them, right? And then when we get to the end of the function, we destroy B, right? So we call the destructor on B, and B goes, oh, cool, my string's not a null pointer. I'm going to release this memory. And then we call the destructor for A, because A is also a stack allocated variable. And we call it a destructor, and A goes, hey, look, well, my string it's not a null pointer either. I'll call it, whoops. Now we have a double free, because the same piece of memory has been freed twice. So the lesson here is that the default copy constructor is often wrong. And something that is really, really important is to always explicitly set constructors, right? Because C++ will give you this default behavior. It's probably not what you want. And because if you just leave the constructors in there, it's just going to do the wrong thing silently. And you're going to be like, why is my program crashing? A good policy is just to always declare your copy constructors, your move constructors. Whoops. If you're not planning on actually copying this class around, right, you can imagine that you're not going to copy the memory of like an actor or copy the memory of like some class you might have thought of. You can actually delete the copy constructors, right, with equals delete. You can delete the move constructor, which I'll talk about in a moment. This basically prevents you from copying the class, right? So now the compiler will not let us copy the class. It also won't let us assign into it or anything like that. It'll be like, nope, this is an error. Unreal has a macro for this. It's called UE non-copyable. So if you're doing Unreal C++, you just whack this UE non-copyable and the class name in there, and it will just delete the constructors for you, and then you won't accidentally make bad code that is going to be bad. I'm not going to go through that example because we are like drastically running out of time. So, you know what? I will put it in. Oh God, no! Swap, please. I will go and get it for you though. So I'm going to put it. Oh my God. Oh no, where do we go? We got here. Yep. All right. What? I'm going to let me copy the. Okay, fine. Okay, cool. Okay, what is the move constructor? Real quick. The copy constructor copies the contents of a target object to a new one, right? So if you imagine that you have an object that allocates like a megabyte of memory, and you copy that object, you will want your copy constructor to basically copy the whole megabyte of memory. The move constructor will move the contents, and what this means is it's kind of like, I like to think of it as stealing, right? So you've got this object that allocates a megabyte of memory, and you use the move constructor to like steal the pointer out of it, and then you set the pointer in the old one to nothing, right? So that when its destructor runs, it won't try and release the memory. And you can imagine that stealing the pointer this way is much cheaper than copying a whole megabyte of memory when you run the copy constructor, right? And so, we try and take advantage of that if we've got classes that are doing like large dynamic allocations of memory. You will also have, if the move constructor is not deleted, you're also going to get a few default assignment operators. That's what makes like B equals A, where B is not just being declared as a new variable work. And they're pretty much what you expect. You either copy the target into a new thing, or you move the contents of a target into that one. It's basically the same thing. It's just, you're not constructing a new object. Okay. All right, let's go into... more stuff. All right. Okay, so we can define our own copy constructors and our own move constructors so that we get the correct semantics for a particular class. So in this case, we've got a test class. It's got a pointer to an int. When we construct this class, we're going to say, we want to make a new int on the heap, and we're going to set it to this value. When we destroy the class, we're going to delete the memory we've allocated. Adding a little handy function here so we can make it easy just to get the integer value out in a safe way. And then we've got our copy and move constructors. And this is, if you're doing lots of like custom copy and move constructors, you will see this pattern a lot. It's very similar between when you've got like these custom constructors. So if we're copying from another ftest class, what we want to do is we want to allocate our own copy, our own int, and we're going to set the int to the value of a in the other class. Fairly straightforward. If we're using the move constructor, we want to steal the pointer from the other class, not the value. We're going to steal the pointer, and then we're going to set the other classes or the other instances a field to null pointer. And in this case, we're clearing out the pointer, but actually the only thing we care about is preventing the other class from running at its destructor. So you can imagine, excuse me, you can imagine if the class has multiple pointers, right, it might actually be cheaper to just steal the pointers and then just set a flag instead of clearing out all the pointers in the other class. You just set a flag saying, I don't want to clear anything I've stolen. It's been moved from, it's fine. Because we have a user-defined move constructor, we also have to define the behavior for the assignment operators. And so basically, let's say we've got an assignment where we're looking at, this for example here is going to be the copy assignment, right? Because we are copying A into B. B already exists. We've got B up here, but we're copying A into B. So we're not using the copy constructor here. We're using the copy assignment operator. And so what this is going to do is basically say, where are we? Right. If we already have a value, right, we're going to release this memory, right? In this case, we definitely have allocated A, right? We want to get rid of it because we no longer need it. We're about to make a new copy, a copy of a new of the other value, right? So then we do the same thing in our copy constructor after we've freed our existing memory, and then you return a pointer to this. That's just kind of like the expected behavior for these assignment operators. Oh, I lose my voice already. Okay, so the move assignment operator. Basically, notice how this doesn't have a new call in it because we don't have to allocate any more memory, right? Again, we're just stealing the existing pointer, setting the other pointer to null so it doesn't run this constructor and returning this, and we're doing our usual typical check. In terms of runtime, in terms of what this looks like at runtime, so you can see here in our code, in our original, before we've done anything, these just have, 5 and 10. We're calling this get_int function that we've written so we can get the actual value out. After we copy it, both A and B equal 5. Each of these has their own memory point. They have their own int in the heap. We can use in the standard library, it's std move. In Unreal Engine, it's called move temp. And we can basically use this to force move semantics on an existing value. And you can see here that after we move, we basically see that A no longer has a value in it, and B has the value of A. And you might be thinking, hang on, didn't we delete the int in the move constructor? We did. In this get_int function up here, we're just doing if A is null pointer, if our value, if we don't actually have a value on the heap because we've deleted it, then just return 0 as a safety, right? So that just makes this nicer to look at, because obviously calling int would be if we didn't do that check and we tried to dereference, we would be dereferencing a null pointer and we get a crash. Cool, that's that done. All right, how are we going for time? Woo! We might be going into lunch a little bit because hopefully no one minds that. Cool, we're at the super important summary slide. Okay, so hopefully what you've got out of this is everything is a block of memory. Everything is a block of memory. I want to stress, everything is a block of memory. Always define or delete your copy and move constructors to avoid unexpected behavior. UE non-copyable is your friend. If you don't know what the copy and move semantics of a class should be, you probably want to put this in your class. Now, you don't have to do it for UObjects, like if you're inheriting from like Actor or anything like that. Unreal is going to delete the copy and move constructors for you. But if you're making just raw classes and using like shared pointers, which we'll get into later, if you're doing that with them, then you want to chuck in UE non-copyable so you don't get weird behavior. If you define the move constructor, then you also have to implement the copy assignment and the move assignment operators if you want those semantics. You probably, most of the time, you're probably not going to have to use you're not going to have to implement a custom move constructor unless you're looking to optimize a class that does a lot of like large dynamic heap memory, where it's going to be more efficient to take advantage of the move constructor instead of just copying. Or it might be a class that you're planning on using literally everywhere, right? You can imagine that the string class in Unreal or the shared pointer class in Unreal, they have move constructors on them because they're used everywhere, right? So it is worth the optimization of writing a move constructor in those cases. And expect it to take a while to get into the mindset of everything as a block of memory. It can take a bit of time. And it is different to most, if not all, other programming languages you are used to. Cool. All right. That is going to wrap up the C++ memory model talk